Hello everyone. In this video, we'll explain the basics of transmission lines in a simple and clear way. In basic circuit analysis methods, connections between elements are assumed to have negligible length. This enabled us, for example, to take for granted that the voltage across a resistor on one side of a circuit was exactly in phase with the source on the other side. But when distances are sufficiently large between source and receiver, time delay effects become appreciable, leading to delay-induced phase differences. Consider a lossless line as shown. By lossless, we mean that all power that is launched into the line at the input end eventually arrives at the output end. A battery having voltage V node is connected to the line by closing switch S1. When the switch is closed, a voltage wave is launched on the line. This voltage does not instantaneously appear everywhere on the line, but rather begins to travel from the battery toward the load resistor R at a certain velocity. Our main objective in this video is to determine this velocity. The wavefront, represented by this vertical dashed line, represents the instantaneous boundary between the section of the line that has been charged to V node and the remaining section that is yet to be charged. It also represents the boundary between the section of the line that carries the charging current I positive and the remaining section that carries no current. Both current and voltage are discontinuous across the wavefront. This means that at the exact boundary of this traveling wavefront, where the wave is just arriving at a certain point along the transmission line, the voltage and the current suddenly jumps from 0 to a certain value. The wavefront moves along the line, and when it reaches the far end, it reflects fully if the resistance R or the load is disconnected, and reflects partially if the load is connected. What else? This is simply a conductor, and every conductor that carries current will always have inductance, even if it is just a straight wire. Because if a current flows through the wire, the magnetic field is generated around the wire in concentric circular path lines. And this magnetic field strength is proportional to the current. And whenever there is a voltage difference between two conductors, electric charges accumulate in them, exactly like a capacitor. Or because a capacitor simply is two conductors separated by distance or an insulating material like air or the electric, thus these two conductors act like a capacitor. And since the transmission line is very long, the capacitance and the inductance are distributed continuously along the entire length of the line. And instead of writing the total capacitance or inductance for the whole line, we express them per meter or per unit length to simplify the analysis. So the conducting transmission line will possess capacitance and inductance that are expressed on a per unit basis. Thus we can construct a model for the transmission line using lumped capacitors and inductors as shown here. Consider now what happens when connecting the same switch's voltage source to the network. On closing the switch at the battery location, current begins to increase in the first inductor, allowing the first capacitor to charge. As this first capacitor approaches full charge, current in the second inductor begins to increase, allowing the second capacitor to charge next. This progressive charging process continues down the network until all capacitors are fully charged. As the charging process continues, the wavefront moves from left to right, and its speed depends on how fast each inductor can reach its full current state, and simultaneously by how fast each capacitor is able to charge to full voltage. The wave is faster if the values of the inductance and the capacitance are lower. Therefore, we expect the wave velocity to be inversely proportional to a function involving the product of inductance and the capacitance, which is in lossless transmission line V equal 1 divided by square root LC, where L and C, the inductance and the capacitance, are specified per unit length. Now, to derive the equations, we will consider a small segment of the transmission line, and this segment contains inductance. This segment contains inductance and the capacitance per unit length, and due to the limited conductivity of the conductors, the segment also possesses series resistance R, which causes power loss. Additionally, the leakage current through the dielectric between the conductors is represented by the shunt conductance G. Both series resistance and the shunt conductance are responsible for power loss along the line. Now, to derive the differential equations, we apply Kirchhoff's voltage law and the current law to this segment. Finally, by making the segment smaller and smaller approaching zero, we obtain two differential equations that describe how voltage and the current varies with distance along the transmission line. We begin with voltage with Kirchhoff's voltage law. Here the voltage V minus V plus delta V is equal to the voltage across this resistance, which is the resistance times the current, half R delta Z times I, plus the voltage across this inductor, which is the inductance times the partial derivative of the current with respect to time, half L delta Z partial I partial T. Here we're taking the partial derivative because the current is not a function in time only, but it is a function in time and position Z. So we take the partial derivative with respect to time. Plus here the same, but put in mind that the current become I plus delta I. So the half L delta Z times the partial derivative of I plus delta I with respect to time, plus half R delta Z times I plus delta I. Here these will cancel out, dividing all by Z and simplifying the equation, we get this. Simplifying it more, we get this. Delta V delta Z equal negative Ri plus L partial T plus half L partial delta I partial T plus half R delta I. Now the incremental voltage is equal to the voltage. The incremental voltage is equal to the rate of change of the voltage with respect to the distance times the incremental distance. Also, the incremental current is equal to the rate of change of the current with respect to the distance times the incremental distance. So we substitute these delta V, delta Z and delta I with these two equations. We get this equation. Now, by taking the limit as delta Z approaches zero, because again we want very small tiny segment of the transmission line, so delta Z approaches zero. This term will cancel and the equation becomes this: partial V partial Z equal negative Ri plus L partial I partial T. Now applying the Kirchhoff current law into this node, I is entering the node, so I equal to Ig plus Ic plus I plus delta I. Simplifying, delta I is equal to negative Ig plus Ic. Now Ig is the current through the conductance, which is the voltage across the conductance times the conductance itself, because the conductance is simply the inverse of the resistance. And what is the voltage? Here the voltage V increased by delta V over this entire distance, so it will increase by delta V over 2 in the midpoint, at the midpoint of the distance. So negative the conductance G delta Z times V plus delta V over 2 plus the plus the current IC, which is the capacitance times the partial derivative of the voltage across the capacitor with respect to time. C delta Z partial V plus delta V over 2 with respect to time. We simplify, we get this equation. Again, we substitute delta I, delta Z, and delta V with these two equations. We get this. Taking again the limit of delta Z approaching 0, we end with this second equation. Partial I partial Z minus GV plus C partial V partial T. Now we take the second partial derivative of the two equations with respect to the position Z. We begin with the first equation, with this first equation. So partial 2 partial V, or the second partial derivative of the voltage with respect to the distance, is equal to negative R partial I partial Z minus L partial 2I partial T partial Z. And we already know what partial I partial Z is equal to. So we substitute this partial I partial Z and this with this equation. We get this equation, simplifying the equation more and more until we end eventually with this 4. This is the first equation of the two equations we are looking for the transmission line. Now taking the second partial derivative of the second equation with respect to the distance, we get again, and simplifying, we get again this 4, this second equation. So these are the two equations for any transmission line. But for the lossless transmission line, R and G, the resistance and the conductance becomes 0. So these equations will simplify out to these two equations. The first one, the second partial derivative of the voltage with respect to the distance is equal to the inductance times the capacitance times the second partial derivative of the voltage with respect to the time. In mathematics, the general or the standard wave equation that describes all waves is this, which says that the second partial derivative of the wave function y with respect to the position is equal to 1 over the wave velocity squared times the second partial derivative of the wave function y with respect to time. If we compare our equation with this standard equation, we notice that 1 over v square is equal to LC. So the wave velocity is equal to 1 over square root LC. This is only for lossless transmission line. We can simply say that the velocity is equal to the distance traveled over the time taken, and any wave has a wavelength lambda, which is the distance that the wave travels to complete one oscillation, while completing one oscillation, and also has a periodic time t, which is the time taken to complete one oscillation. So the velocity simply is distance over time, which is the wavelength over the time t, which is 2 pi over beta divided by 2 pi over omega. So it is omega over beta. The omega represents the angular velocity, and beta represents the phase constant, which is the rate of change of the wave phase with respect to distance. This is the velocity of the wave for if there is a power loss in the wave. But in the lossless transmission line, the velocity is equal to 1 over square root LC, also equal to omega over beta. But if there is a loss in the power, the velocity is only this. And that's it. Thank you.